Hello folks, welcome back to Trigonometry. Today we are going to look at the inverse trig functions. When you guys take an algebra class, you learn about functions and their inverses. And so today we're going to apply that knowledge specifically to trig functions. We know that for a function, if you look at its graph, it's going to pass the vertical line test. And what that means, if it passes the vertical line test, then that means that each x or input, each x value or input has exactly one y value or output. Well, we can take these functions and we can analyze them a little further. If a function passes the horizontal line test, meaning each y value has only one x value associated with it, then the function is 1-to-1. And has an inverse. Okay, so we learned about those in algebra classes. But we're going to apply that knowledge here to the trig functions. We know that y equals sine x, y equals cosine x, and y equals tan x are all functions. But right now, as they're written, they're not 1-to-1. So because if you look at y equals sine x, you've got that sine wave. It passes the vertical line test, but does not pass the horizontal line test, so it's not 1-to-1. If you look at cosine x, it's basically sine x translated by pi over 2. It passes the vertical line test, it's a function, but does not pass the horizontal line test. And if you look at tangent, one piece of it may pass the horizontal line test, but it's periodic, so you've got several pieces, so ultimately it does not pass the horizontal line test. So none of these are 1-to-1 unless we restrict the domain. If we take these functions and restrict the domain and say, okay, we're looking specifically at this function here with this domain, then we have 1-to-1 in an inverse. And that's what we're going to do. We're going to take each of those, restrict the domains, and then make them 1-to-1. Make them functions that are 1-to-1 so that they do have an inverse, and then explore what those inverses look like and what some of the properties are for those inverses. Okay, so let's start with y equals sine x. Y equals sine x, you have that nice sine wave. Okay, right now the way it is, it's not 1-to-1. But what they have done is they've come up with a convention where we go ahead and take just a piece of the sine wave. We start at negative pi over 2, and we take the piece all the way to positive pi over 2. And we just look at that. We look at y equals sine x, where x is found in the interval from negative pi over 2 to pi over 2. And we use that piece to do our inverse. Now notice that piece passes the horizontal line test. Passes the vertical line test, it's a function, which is part of sine x, which is a function. And it also passes the horizontal line test. Now you could have used other pieces, but just convention goes ahead and uses this piece. I think it's pretty handy because it's hanging out here near the axes, and it gives you that one-to-one feature. It gives you a good spread of values and everything. So we'll do that. We'll focus on that. All right, so let's look at what the graphs look like. All right, if we had, let's do x sine x. If you have x is negative pi over 2, sine x is negative 1. Negative pi over 2 is roughly negative 1.57. If x is negative pi over 3, or roughly negative 1.05, then sine x is negative square root of 3 over 2, or around negative 0.87. If x is negative pi over 4, or roughly negative 0.79, then sine x is negative square root of 2 over 2, or negative 0.71. If x is negative pi over 6, or roughly negative 0.52, then the sine is negative 1/2, or roughly negative 0.5. If x is 0, sine of 0 is 0. If we have pi over 6, it's like having positive 0.52. Then we're going to have positive 1/2, or 0.5. And then same thing, if we go pi over 4, pi over 3, pi over 2, can work with all those. This is all old news. You guys have done all this before, so I'm not going to harp on it too much. But what we're going to do is use these values to help us with finding our inverse. Okay. Now, now to find the inverse, this is the x, this is the chart for sine x over this interval right here, from negative pi over 2 to pi over 2. Now to find the inverse, we can reverse the xy coordinates. We're starting with y equals sine x, where the domain is negative pi over 2 to pi over 2, and the range is negative 1 to 1. But to do the inverse, you swap the x's and y's. So then you end up with y equals inverse of x. Whoops, let me erase that. Inverse sine of x. So then you're going to swap, so that means now your x values are going to go over negative 1 to 1. What was the range of your sine x is going to be the domain of your inverse sine. And what was the domain of your sine x is going to be the range of your inverse sine. You swap your x's and y's. And that can be used to also get your graph and whatnot. So you reverse those xy coordinates, and there you go. And you've got still those same limitations with your domain and range. It's just they're swapped now. Domain became range, range became domain. Now, real quick side note, inverse sine could also be called the arc sine. If you see arc sine of x, that's what they're talking about. They're talking about the inverse sine. Alright, well, let's do a little bit of plotting. Let's see what this looks like when we put it on the graph. Alright, let's mark this off. Let's make this 1. Let's make this 2. Let's make this -1. Let's make this -2. We got 1, 2. We got -1 and -2. Alright. Now I'm going to do in, I think I'll do in purple what y equals sine x looks like. So y equals sine x, around -1.57, you have -1, right here. Around -1.05, you have -0.87. There. Around -0.79, you've got -0.71. So about there. -0.52, you got -0.5. At 0, you got 0. At 0.52, you've got 0.5. At 0.79, you've got 0.71. At 1.05, you got 0.87. And at 1.57, you've got 1. Alright, so that's the sine curve for you. We're limiting it so it stops right there. Okay. Now when we go to do the inverse, we do reversal. We swap the x's and y's. So let's do that in orange. Let's do the arc sine in orange. Which is the same thing as saying the inverse sine. Okay, so the inverse sine at -1, you've got -1.57. At -1.05, or at -0.87, you've got -1.05. At -0.71, you've got -0.79. At -0.5, you've got -0.52. At 0, you got 0. At 0.5, you've got 0.52. At 0.71, you've got 0.79. At 0.87, you've got 1.05. And at 1, you've got 1.57. Okay, so you connect the dots on that. You basically got a sine curve here too, but it's kind of rotated in a way. But there's your arc sine. It is a function. It passes the vertical line test, and it's also 1-to-1. Passes the horizontal line test. Now, a really interesting thing about functions and their inverses is if you draw the line y equals x, the function and its inverse will be reflections across y equals x. So if you If you take the orange and reflect it across y equals x, you'll get the purple. Or vice versa, if you take the purple and reflect it across y equals x, you'll get the orange. Two nice mirror images across y equals x. And that's going to be true for any function in its inverse, not just trig functions. Okay, so there's a glimpse into what it looks like. Now, what can you do with that knowledge? Well, let's say you're given a problem and they say the inverse sign, find the inverse sign of square root of 3 over 2. Okay, so let's say the inverse sign of square root of 3 over 2 equals a. So I'm just making up something. So basically, the sine of a has to equal square root of 3 over 2. So you're trying to find a, the angle between negative pi over 2 and pi over 2, where this is true. Because remember, we restricted the inverse sign. The inverse sign has domain of negative 1 to 1, range of negative pi over 2 to pi over 2. So inverse sign of square root of 3 over 2 equals a. It can only equal, its y here can only fall from negative pi over 2 to pi over 2. So we got to figure out which angle makes that happen. And if you think about it, theta would be pi over 3 to make that happen. Right. Now if you had something like inverse sine or arc sine of negative square root of 2 over 2, basically you're saying that the sine of theta equals negative square root of 2 over 2. So you got to find theta between negative pi over 2 and pi over 2. So theta for this would be negative pi over 4. So that's how you work that. Alright, now just like sine, the other trig functions, same kind of thinking. You can do inverse for cosine, you can do inverse for tangent, you can even do inverse for secant, cosecant, and cotangent. And we'll get to those. Alright, let's look at cosine next. Alright, if you look at y equals cosine x, that graph is basically the sine graph shifted. Now right now, it's a function, but it's not one-to-one. But if we go ahead and restrict the domain, let's start at 0 and go to pi. Then we have this piece here of the cosine function. That is one-to-one. It does pass the horizontal line test. So if we go ahead and take y equals cosine x and limit the domain to go from 0 to pi, the range will go, including pi, the range will go from negative 1 to 1. So then when we swap x and y to find the inverse, also referred to as the arc cosine, then the domain will go negative 1 to 1, and the range will go 0 to pi. So just like with the arc sine, if you know your x's and y's for the cosine function, you can swap them and get your x's and y's for the arc cosine. what color scheme did I do? I'll be consistent. I had blue, purple, and then orange. Okay, so I'll do that again. All right, purple will be y equals cosine x. And then orange will be y equals arc cosine x. Same thing as saying inverse cosine x. Alright, let's mark this off again. We're going to go like from -1 to, let's see, +1's right here. +2's right here. +3's right here. That's probably as high as we need to go. Okay, so if we're looking at 0 to pi, for cosine, we'll have 0, comma, oh, I didn't mark off this direction, hang on. Go up 1, 2, up here's 3, -1, -2, and so on. I don't think I need to go any further than that. Okay, so cosine, we got 0, comma 1. Around 0.52, we've got 0.87. Around 0.79, we have 0.71. Around 1.05, we have 0.5. Around 1.57, we have 0. Around 2.09, we have -1.5. Around 2.36, we have -0.71. (2.62), we have -0.87. Around 3.14, or pi, we have -1. Alright, so the actual cosine under the restricted space from 0 to pi looks like this. Okay, and now for the arc cosine, we swap them. We have a 1, comma 0 right here. We have a 0.87, comma 0.52, so about right here. 0.71, comma 0.79. .5, comma 1.05. A 0, comma 1.57. -0.5 and a 2.09. -0.71 and a 2.36. A -0.87 and a 2.62. Oop, I'm running into my words. -1 and a 3.14, so it's up there. But you guys can see, get the idea. Okay, so there's the inverse of that one. And notice again that if you look at the line y equals x, you got symmetry. If you reflect the orange one across y equals x, you got the purple one, or vice versa. So there's your arc cosine. Alright, so where could this be used? Well, if you have to find the inverse cosine of -1/2, then you're looking at cosine of some theta equals -1/2, but you're finding theta from 0 to pi. So in this case, the theta that fits that would be 2 pi over 3. And now you've been able to, answer that question. All right, let's look at the tangent next. Y equals tangent of x. If you're thinking about tangent, tangent's pi periodic. You have something that looks like this. And these asymptotes, you got negative pi over 2, pi over 2, but this all keeps repeating. So if we want to talk about inverse, we're going to do some restricting again. We're going to restrict to everything from negative pi over 2 to pi over 2. And that way we not only have a function, but we also have one that's 1 to 1. So we're going to restrict to just this part here. So we're going to take y equals tan x with the domain from negative pi over 2 to pi over 2. Of course, it's open interval because pi over 2 and negative pi over 2 are your vertical asymptotes. But your range was negative infinity to infinity. Well, if you want to do a little swapping, there you've got the function that's 1 to 1, so it has an inverse. So you can swap your x and y and get y equals the inverse tan of x, or arctan. Then your domain is going to be negative infinity to infinity, and your range is going to be the negative pi over 2 to pi over 2. So it's going to look kind of like the tangent fell over and is laying on its side. That's basically what it's going to look like. So going back to here, if purple, I used purple, yes, I want to try to be consistent, use the same colors. So if purple is y equals tan x, you got, let's see, let's mark this off, and then orange is going to be y equals arctan x. Mark this off. You got negative 1, 2, negative 2, and so on. Probably don't need any more than that. You got positive 1, positive 2, positive 1 going up, positive 2 going up, negative 1 going down, negative 2 going down. Alright, so tan at negative pi over 2 and pi over 2, you have the vertical asymptotes. So around negative 1.57 vertical asymptote, and around positive 1.57. You have vertical asymptote. Alright, and then you've got the 0, 0 here in the middle. And then at around negative 0.79, you'd have the negative 1, so about right there. And around positive 0.79, you'd have the positive 1 right there. So you've got that nice curve. That. Okay, so that's the tan. The arctan swaps the x's and y's. So now instead of vertical asymptotes where x is negative pi over 2 and where x is positive pi over 2, you're going to have horizontal asymptotes where y is negative pi over 2 and y is positive pi over 2. So I'm in my orange color. So at y being negative 1.57, I have a horizontal asymptote. At y being positive 1.57, I'm going to have a horizontal asymptote. And then instead of having negative 0.79 comma negative 1 like I did here, I'm going to have negative 1 comma negative 0.79. And instead of having 0.79 comma 1 like I did there, I'm going to have 1 comma 0.79. And my curve's going to end up going like this. Because again, there's a reflection across y equals x. I mean, I'm not drawing this perfectly, but you know, if you really had a ruler and everything and drew some more points, drew more points than I did, you would see a reflection across that y equals x. Purple across y equals x gives you orange, or orange across y equals x gives you purple. So you get that nice curvy type fun there. But that's your arctan. Okay, so like if you were asked to find, you know, inverse tan of negative 1, you've got tangent of theta equals negative 1. So you're trying to find theta that makes this work between negative pi over 2 and pi over 2. And you get that theta would be negative pi over 4. Okay? Alright, now let's go ahead and do a couple problems where we're using these and using some compositions. And then after that, we'll also talk about like inverse cosecant, inverse cotangent, inverse secant as well. Alright, just real quickly, let's do first a calculator type question. Like, let's say you have to find the inverse cosine of 1/3. You can actually do that on your calculator. If you pull up your calculator, let's make sure it's in radian mode, because we've been doing everything in radians and such. If we go ahead and do that, if you look at your sine, cosine, tangent buttons, you've got the sine with the -1, the cosine -1, tangent -1. That does not mean, that's not really an exponent meaning 1 over. That's the inverse sine, inverse cosine, inverse tan. So that's where you're going to be able to do your arc sine, arc cosine, arc tangent. So if you hit second cosine, it'll give you inverse, and then put in the 1 divided by 3, hit enter, and it gives you your value. So basically, the cosine of that value to the cosine of 1.230959417 should give you something awfully close to 1/3. Which it's rounded, so you know down the line it's rounded, but 0.33333, you know, it's giving you basically back 1/3. If you try to do something that's outside of the domain or range, it's going to balk and go, well, I can't do that. Like if you try to do inverse sine of -2, you're basically trying to figure out, you know, sine of what theta gives you -2. Well, the sine of no theta will ever equal -2, because the range of sine goes -1 to 1. So as soon as you hit enter, it's going to give you an error and tell you it's an error in the domain. So I'll quit and go back. But so the calculator is smart enough to see, oh, that's not in the domain, so you can't do that. Alright, now some other situations you could face too. You could end up dealing with compositions of functions. You know, if you're dealing with a function and its inverse, you do the composition, of a function and its inverse will equal equal x. Another way of writing that, you might have seen it written like this instead in the past. Basically, if you plug x into the inverse and then get an answer, and then plug that answer into the function, you'll get back x. Now it also works the other way. You can do the composition of the inverse and the function and get back x. As long as x is in the domain of f. So you got to watch your domains. You got to make sure that you're careful with those. All right. For instance, let's say you have something like the cosine of the inverse cosine of 0.7. Well, if you pull up your calculator here, and let's say you do the inverse cosine of 0.7, get this crazy value. But then if you do the cosine of that, you get back 0.7. So whatever your argument was here, if you do the cosine of the inverse, if you do this composition where the inverse is on the inside and the function is on the outside, it's going to equal whatever the original input was. So in this case, the 0.7. Whoops, excuse me. Now you have to be really careful though, because like let's say you have inverse sine of sine of pi. Well, sine of pi is 0. So you're looking at the inverse sine of 0. You're going to get 0. Because remember, with inverses, you have to limit things. You have to be very careful about dealing your domain and range. Like sine of pi, you can get 0, but then you have, you're doing inverse sine of 0, you're going to get back the 0, not pi, because the inverse sine is limited from negative pi over 2 to pi over 2. You're not going to find the sine of pi there in the you're limiting your values differently. It's kind of interesting. Let's say you do cosine of the inverse cosine of negative 1.2. Well, negative 1.2 is not in the domain in the first place. The domain for the inverse cosine is negative 1 to 1. So that one can't even be done. Because remember, the domain of the inverse cosine is like the range of the cosine after we've limited it. So negative 1.2 is outside that scope, so that one's not even going to be doable. So those are the kinds of things to think about. Sine of pi, like sine of pi is 0. So we get that. And then you can do inverse sine of 0, because when you're doing the inverse sine, like we limited sine to go from negative pi over 2 to pi over 2, and the range went from negative 1 to 1. On the inverse sine, the domain goes from negative 1 to 1. So we can use 0, but we're not going to... But, so that works. That 0 works. All right. Let's kick it up a notch. Let's say you have something like... There's a couple more of these, and then I'll address the secant and cosecant. Let's say you have something like sine of the inverse tangent of 3/4. You might be like, well, 3/4 isn't on my unit circle, so what the heck do I do? Well, think about inverse tangent of 3/4. If you're doing that, you're going to basically be finding a theta. So, tan of theta is 3/4. Well, when we're doing inverse tan, we've limited things to the negative pi over 2 to pi over 2. So we're basically trying to see, you know, from negative pi over 2 to pi over 2, which angle will give the tan being 3/4. If it's going to be a positive tan, negative pi over 2 to pi over 2, we've got quadrants 1 and 4. If it's going to be a positive tan, a smart trig class, it has to be up here in quadrant 1. So let's sketch a triangle. If this is theta, tan is opposite over adjacent, so hypotenuse is going to be 5. And then from there, you're finding the sine of that theta. Because you're doing the inverse tan of 3/4 is equal to some theta, so you're basically doing the sine of that same theta, and that's going to be opposite over hypotenuse, so 3/5. Alright, let's say you're doing the cosine of the inverse sine of negative 1/2. So you got inverse sine of negative 1/2 is equal to some theta. So sine of some theta is negative 1/2. Now we've limited it though from negative pi over 2 to pi over 2, so we're looking at limited the sine, negative pi over 2 to pi over 2. So we're somewhere in quadrants 1 or 4. But if the sine's negative, then we must be down here in quadrant 4. So look at theta here. So negative 1/2, we're looking at opposite over hypotenuse for the sine. And so adjacent must be square root of 3. So then you're basically finding the cosine of the theta, and that's adjacent over hypotenuse, so square root of 3 over 2. Alright, then one more of these. Let's say they tell you that x is greater than 0, x is positive. They want you to write the secant of inverse tan of x as an algebraic expression in x. Alright, if x is positive, let's see, tan, inverse tan, we limit it from negative pi over 2 to pi over 2. So it has to be over here somewhere. X is positive. We're looking at some tan of theta equals x. So where is the tan equal to something positive? And that would be up here. So we got, if tan of theta is x, it's like saying x over 1. So opposite over adjacent is x and 1. So the hypotenuse must be the square root of 1 plus x squared. So the cosine of that theta is going to be 1 over square root of 1 plus x squared, which means the secant of that theta is going to be the square root of 1 plus x squared. So that's how that works. Okay. Now finally, like I said, we're going to talk a little bit more about the others. You also have arc cotan, arc secant, arc cosecant. If you're dealing with the inverse cotan, that's arc cotan. The domain of that's negative infinity to infinity. The interval, you're dealing with 0 to pi. So you're looking at quadrants 1 and 2 on the unit circle. For inverse secant, you got negative infinity to negative 1, union 1 to infinity. You got 0 to pi over 2, union pi over 2 to pi. And you're dealing with quadrants 1 and 2. And then for inverse cosecant, you're dealing with negative infinity to negative 1, union 1 to infinity, and negative pi over 2 to 0, union 0 to pi over 2, in quadrants 1 and 4. Okay. So if you basically look at your cotan graph over 0 to pi, and then do the reflection across y equals x, you know, you're swapping your x and y coordinates. So you end up where cotan would be the domain is 0 to pi, with arc cotan the range is 0 to pi, you know, and so forth. And then secant, that's the reciprocal of cosine, so you're limiting it from 0 to pi, just like you would with cosine. And then cosecant, that's the reciprocal of sine, so you're limiting it from negative pi over 2 to pi over 2, just like you would with sine. But then you have to include the fact that there's vertical asymptotes and stuff, so that's why you get gaps or breaks inside of these range intervals here. But you've got those, and you might be asked to find some of the degree values of some of those. Like let's say you have something like theta is the inverse cosecant of negative square root of 2. So let's say you have something like that. Alright. Inverse cosecant has to be in quadrant 1 or 4. And since we're dealing with negative square root of 2, it must be in quadrant 4. Must be somewhere in there. And you're basically saying, okay, cosecant of theta is going to equal negative square root of 2, right? Well, if that's true, then really it's saying 1 over sine of theta equals negative square root of 2. So sine theta equals negative 1 over square root of 2. And you have to decide, well, where is that true? Where is it true that the sine of theta equals negative 1 over square root of 2? Well, if you rationalize the denominator, you get negative square root of 2 over 2. Maybe now it'll look even more familiar. That should look more like something that you've done. Now we're in quadrant 4, and where does the sine come out to negative square root of 2 over 2? Well, it comes out to that at, you could either say negative pi over 4 in radians, or you could say negative 45 degrees. So that's how you can deal with that inverse cosecant there. All right, what if you have something like y equals inverse secant of negative 4? Well, it's like saying that the secant of y equals negative 4. It's basically what you're saying there. But you know, inverse secant the same thing as saying that 1 over the cosine of y equals negative 4. So you're looking at, well, where does the cosine of y equal negative 1/4? Where does that happen? Let's pull up our calculator. And let's see. What mode are we in? We're in radians, so it's going to give us our answer in radians. So if we do inverse cosine of negative 1/4, whoops, hit the wrong button. We get this. We get 1.82347652. So that gives us our answer, basically. Basically, it's giving us our theta, our angle here. And that falls within the interval that inverse secant's allowed to fall into. Alright, let's do one more. Let's say theta equals arc cotan of negative 0.2528. Okay, arc cotan, that's the inverse cotangent. But that's also like saying that theta equals, or like cotangent of theta equals negative 0.2528. I have an interesting process with this, because it's like saying, alright, 1 over tan of theta equals negative 0.2528. So tan of theta equals negative 1 over 0.2528. So let's put that in our calculator. So let's do the inverse tan of negative 1 divided by 0.2528. Let's see what it gives us. It gives us negative 1.323184811. Problem with that is it's found in quadrant 4. But inverse cotangent is only found in quadrants 1 and 2. So we get negative 323184111. 323184111. Here, I'm trying to get this written down. Let's see here. So we got negative 1 point that. So we're getting that theta is that. But we found that by doing the inverse tan. We have a problem here. This is a quadrant 4 angle. We're going to run into this with trying to do arc cotangent sometimes. This is a quadrant 4 angle because when you're putting in your calculator, you're putting in that tangent value. But you got to think about the fact that cotangent, inverse cotangent though, is found in 1 or 2. And that's originally what we're trying to find, is inverse cotan. And since this is negative, we're looking at a quadrant 2 angle. So if you think about it, if they're giving us an angle that's in quadrant 4, and we need the quadrant 2 up here, we can just add 180 and get it. So let's go back to our calculator. And add, well, since either 180 degrees or, same thing as 180 degrees is pi. And since we are in radians, we need to go ahead and add pi to that and see what that gives us. And that gives us the 1.818408, etc. Or if you were in degrees, let's say you were in degree mode. If you're doing that, if you did the inverse tan of negative 1.25, dang it, there should be a division symbol there. 0.2528. Get that, and then add 180 degrees to that, and you get 104.1871349 degrees. So that's just something to think about. Just watch your quadrants, because like inverse sine and inverse cosecant are both found in quadrants 1 and 4, Inverse cosine, inverse secant are both found in quadrants 1 and 2, so you don't really run into these kinds of issues so much, but inverse tan and inverse cotan, inverse tan is found in quadrants 1 and 4, while inverse cotan is found in quadrants 1 and 2, so you do have to watch out when you're solving these problems, because if you're doing arc cotan and you switch to tan, you're dealing with negative angles, you're going to end up with the wrong quadrant. Then you might have to add 180 degrees or pi to help adjust. So I just want to warn you of that. Okay, well that's enough about inverses. You'll have plenty of fun, working problems and graphing with those. And I'm sure that'll keep you busy until I see you next time.